All right, let's get right into it. If you're a technician working with any kind of electronic system, this is going to be your bedrock. We're talking about something way more important than just paperwork. It's about making sure you can do your job safely and, actually get it done right. So today, we're breaking down test equipment administration. So we all know that having the right tool, whether it's a scope or a multimeter, is absolutely essential. But I want you to think about this for a second. What could possibly be more important than just having that tool in your bag? And there it is, it's knowing you can trust it. It's that gut level confidence that when your meter says 120 volts, it is actually 120 volts. That idea, that simple concept of trust, is the foundation for everything we're about to talk about. It impacts every single repair, every diagnostic, and most importantly, your safety. So here's our game plan for this explainer. We're going to start with the big picture, the why behind all of this. Then we'll get into how we name and classify all this gear. After that, we'll decode those super important calibration labels, cover maintenance and safety, and then see how it all comes together when you're taking measurements. And don't worry, we'll wrap it all up with a quick recap and some practice questions to get you prepped for your exam. Okay, first things first, the big picture. Why do we have to deal with all these procedures? Well, it all comes down to one core idea: mission readiness. Simple as that. When a piece of critical gear goes down, you have to be able to trust your instruments to find that problem fast and find it accurately. This isn't just about making your life easier, it's about reliability, and that's what keeps you and everyone around you safe. Right, so imagine trying to keep track of thousands and thousands of pieces of equipment across the entire fleet. You'd need a common language, right? So think of this next part as learning the basic grammar for identifying every single tool you're going to use. And that common language is called JETDES, the Joint Electronics Type Designation System. It's basically a standardized naming system that every single branch of the military uses. So a specific oscilloscope isn't just a random model number, it gets a universal JETDES identifier. This is huge because it means a technician in the Navy and a technician in the Air Force are talking about the exact same piece of gear. Everyone is on the same page. Now, JETDS helps sort all this equipment into two big families. First, you've got GPET, which stands for General Purpose Electronic Test Equipment. Your classic multimeter is a perfect example. It's a jack of all trades you can use on tons of different systems. Then you have SPET, or Special Purpose. This stuff is designed to test one and only one specific piece of equipment, like a particular radar system. Knowing the difference here is key because it changes how the equipment is managed, maintained, and even procured. So if JDDS is like the name on a tool's birth certificate, then SCLSIS is the official census for the entire fleet. SCLSIS, that's the Ship Configuration and Logistics Support Information System, is the master inventory program. On a ship that has literally thousands of pieces of gear, SCLSIS is what tells you exactly what you have, where it is, and its current configuration. It's the backbone of logistics. Okay, we've been talking a lot about trusting your equipment. Well, this next part is how you verify that trust. The answer is calibration labels. These little stickers are your cheat sheet. They tell you the exact status of any instrument with just a quick glance. Now, before we dive into the labels themselves, we need to get one thing crystal clear: the difference between repair and calibration. Repair is about making something work. A knob is busted, you fix it. That's repair. It's about functionality. Calibration, on the other hand, is about making sure it works correctly. It's all about accuracy, aligning that instrument against a super precise known standard. And here's the golden rule: a tool has to be fully repaired and functional before it can even be sent for calibration. All right, now this slide shows you the whole family of labels. I know, it looks like a lot, but don't get overwhelmed. Just think of it like a visual dictionary. Every color, every phrase has a very specific meaning. One look tells you if a piece of gear is good to go, if it has some limitations, or if it's flat out of service. So let's break down the most common ones you'll see every day. First up, the one you want to see, the simple black on white calibrated label. That's your green light. It's accurate, it's in tolerance, you're good to go. Next is the red on white, refer to report. This means it's still calibrated, but if you're doing really high precision work, you need to look at the report to get the exact measurement values. Then there's the black on yellow special calibration label. When you see yellow, think caution. It means the tool has a specific limitation. Maybe one of its ranges is a little off. The details will be written right on the tag. And finally, the big one, the black on red rejected tag. This is a hard stop. Do not use this tool. It means it failed calibration and it can't be repaired. So we know how to identify our gear and how to verify that we can trust it. Now let's talk about keeping it that way. This section is all about the practical, hands-on care for your instruments, and even more importantly, the rules that are going to keep you safe while you're using them.
You've got to remember, these are precision instruments, and they can be surprisingly fragile. So, what are the three big invisible dangers that can completely wreck their calibration or even destroy them?
So those three dangers are, number one, mechanical shock. Pretty simple. Dropping or even just bumping a meter can knock its sensitive internal parts out of alignment. Number two is strong magnetic fields. Getting a meter too close to a strong magnet can permanently mess up its accuracy. And number three, excessive current. Trying to measure too much current can literally overload and fry the meter's circuits. That's why you always start on the highest range and work your way down. Okay, now for what is by far the most important part of this whole thing, your personal safety. And let's be clear, these are not suggestions, they are hard and fast rules. First and foremost, you do not work on energized circuits alone, ever. You always need a safety observer. Second, whenever it's practical, use only one hand. Why? Because that simple trick can prevent a deadly current from passing across your chest and through your heart. Third, always make sure your test equipment is properly grounded. And finally, de-energize the circuit before you hook up your test leads or alligator clips. These rules save lives. It's as simple as that.
So, let's connect the dots. Once we've identified our gear, we've verified its calibration, and we've followed every single safety rule, what's the whole point? Well, it's to take accurate, reliable measurements. Let's look at how all these principles come together in a classic precision measurement circuit.
This right here is a Wheatstone bridge. Now, it might look a little old school, but it's a circuit designed for making extremely precise resistance measurements, way more accurate than your standard ohm meter. The whole idea is actually pretty simple. Step 1, you apply a voltage. Step 2, you start adjusting 3 of the known variable resistors. And step 3, you just keep tweaking them until that sensitive meter in the middle, the galvanometer, reads exactly 0. When it hits 0, the bridge is officially balanced. So why does this work? It's pretty cool, actually. When that meter reads 0, it means there's no voltage difference between the two sides of the bridge. The voltage ratio on the left branch is perfectly identical to the ratio on the right branch. Since there's no difference, no current can flow across the middle. And because you know the exact resistance values of the 3 resistors you adjusted, you can use a simple formula to calculate that unknown resistor, Rx, with incredible precision. Okay, wow, we have covered a ton of ground, from the high-level admin stuff all the way down to specific measurement circuits. So now it's time to make sure all that information sticks. Let's run through a real quick recap and then hit a few practice questions to make sure you're ready to go. All right, let's do a rapid-fire review. JEDTS, that's the standardized naming system. GPETE, general purpose, tests lots of systems. SPETE, special purpose, tests just one. Calibration, that's all about accuracy, aligning to a known standard. Wheatstone bridge, you use that for super precise resistance measurements. And SCLSIS, that's the master inventory system for all the gear. Got it? Good. Okay, practice question number 1. Take a second and think about it. What's the main functional difference between general purpose and special purpose electronic test equipment? The answer is its scope. GPET is versatile and tests many different systems, while SPET is designed for only one specific system. All right, question 2. Picture this. You're in the shop, you grab a multimeter, and it's got that black on yellow special calibration tag. What's your immediate reaction? What do? It means you have to use it with caution. You absolutely must read the tag to understand what its limitations are, because some part of it, maybe a specific range, is not within tolerance. And for our last question, and this is the most important one, what is the absolute number 1 non-negotiable safety rule you follow before you even think about working on an energized circuit? The answer is, do not work alone. You always have a qualified safety observer with you. Okay, that's our deep dive on test equipment administration. If you really get these concepts down and never forget those safety rules, you'll be set. Good luck.